So, how do you turn a corner when you're in the middle of nowhere? And I mean really nowhere. In the vacuum of space, there's literally nothing to push against. It's a fascinating problem.
Think about it. Here on Earth, if you want to change direction, it's pretty straightforward. You turn your car's wheels against the asphalt, you use a boat's rudder to push against the water, or you bank a plane's wings to bite into the air. All of these things rely on pushing against, well, something. But in space, there's nothing. So how in the world do you steer?
Right. On Earth, we are constantly pushing against an external medium, whether we realize it or not. But in space, you've got to bring your own push. And the solution? Oh, it comes from one of the most fundamental, elegant laws of physics you can think of. Newton's third law. You know the one. For every action, there is an equal and opposite reaction. That push is delivered by a seriously vital and ingenious piece of engineering. So let's meet the hero of our story, the reaction control system, or as everyone calls it, the RCS.
Okay, so what is it? At its core, an RCS is basically a network of small thrusters. They fire these incredibly precise little jets of gas, and thanks to our friend Newton, pushing that gas out in one direction creates an equal and opposite reaction that nudges the spacecraft. This system allows for two very different but equally important types of movement.
First up is attitude control. The easiest way to think about this is to just use your own head. If you tilt it from shoulder to shoulder, that's roll. If you nod up and down like you're saying yes, that's pitch. And if you shake your head no, well, that's yaw. The RCS lets a spacecraft rotate along any of these three axes without actually moving from its spot. It's all about pointing.
The second key function is translation. Now, this is about moving the entire ship from point A to point B. The best analogy? Imagine you're in a swimming pool. If you push off the wall with your feet, you glide sideways across the water without tumbling over, right? That's translation. An RCS can push a spacecraft left, right, up, or down, all while keeping it pointed in the exact same direction.
And the Gemini spacecraft, wow, it was an absolute pioneer in mastering this stuff. Its designers were so clever. They placed some thrusters way out from the center of mass to create torque for rotation, the pointing. And they put other thrusters closer to the center to push the whole craft for a translation. This was revolutionary. For the very first time, it gave astronauts the ability to truly fly in space, to actually rendezvous and dock with another vehicle. Those skills were absolutely essential if we were ever going to get to the moon. But an RCS isn't just for making turns and parking next to another spaceship. No. It's the spacecraft's ultimate multi-tool. It's essential for the mission's success and, frankly, for survival.
This system is a true workhorse. It does something called station keeping, which is just making tiny little adjustments to fight against orbital decay. It's used to orient the spacecraft, whether that's pointing a communications antenna back at Earth or aiming a telescope at a galaxy billions of light years away. It can even act as a backup system to kickstart the journey home, and as we just saw with Gemini, it handles docking, a maneuver that requires millimeter precision when you have two massive vehicles hurtling through space at thousands of miles per hour. Talk about high stakes.
Now, the tech to do all of this didn't just appear overnight. It has a really rich history, and it's evolved with every new generation of spacecraft.
That system on Gemini we talked about, it was a total game changer. It used these powerful hypergolic fuels. That's a fancy word for liquids that ignite the second they touch each other. No spark needed. This gave astronauts the raw power to not just point their spacecraft, but to actually change their orbit. This wasn't just steering anymore. This was flying. And it was a critical step on that long road to the moon.
And speaking of the moon, the Apollo lunar module absolutely relied on its RCS for survival. You've probably seen them, those iconic clusters of 4 little thrusters. Those are the RCS quads. There were 16 of these thrusters in total, and they gave guys like Neil Armstrong and Buzz Aldrin the incredibly delicate control they needed to navigate those final few hundred feet down to the lunar surface, and just as importantly, to lift off again. That system was truly the difference between success and disaster.
Then, of course, came the space shuttle, a much larger and more complex beast. Its RCS had to be way more robust. It had these powerful thrusters built into its nose and also in 2 huge pods at the back. These things were essential for all its orbital jobs, like deploying satellites, and for precisely positioning that massive airframe for the fiery plunge back into the atmosphere.
But there's a catch with all these amazing systems. They all use fuel. And in space, fuel is everything. It's finite. Once you run out, you are just along for the ride. And that limitation has forced engineers to get really clever.
This fuel problem led to a brilliant alternative, at least for attitude control: momentum wheels, or CMGs. Instead of shooting out gas, these things use electricity from solar panels to spin heavy internal flywheels really fast. By changing the speed of these wheels, the spacecraft rotates in the opposite direction. Now, it can't move the ship side to side, it can only do the pointing part. But for that, it doesn't use a single drop of that precious, irreplaceable fuel.
So, the modern approach is often a hybrid one, and the International Space Station is the perfect example. For its routine, day-to-day pointing and staying stable, it relies on these massive, electrically powered momentum wheels. It's basically running on sunshine. But when a big supply ship needs to dock, or they need to make a major orbital adjustment to dodge debris, then they fire up the good old RCS thrusters. It's the best of both worlds: incredible efficiency for the long haul and raw power when you really need it.
Which, it leaves us with one final thought. From the very first tentative little pushes on the Gemini capsule to the decades-long presence on the ISS, the reaction control system has been the unsung hero of spaceflight. But as we start planning for missions at last year's, journeys to Mars and beyond, where there is no refueling stop, how will this fundamental technology of the tiny push have to evolve all over again? That is something to think about.